All right, welcome everybody to our online version of Lecture 6 for electrochemistry. And we're going to divide this one into parts and see how it goes. That way it might be a little bit easier to digest some of the smaller sections. And we'll see how it goes. So electrochemistry, very important in these days, much more important now than it was when I was your age. We have so many more devices that run on stored energy. Your phones, any of the tablets, your laptops, just your wireless headphones, whatever you happen to have, all have some sort of stored electrical energy, and it's one of the most common types of energy that we see today. We see it primarily in the form of batteries. There are also things called ultracapacitors. There are fuel cells that all store energy in one form or another. Now, what happens to store that energy is we have electrochemical reactions. Rather than necessarily transferring atoms from one species to another, we're actually transferring electrons from one substance to another. And if we can grab those electrons in the process of transferring, then we can route them through a wire and use them to power a device. And we'll see how that goes here just a little bit later. So when we have one of these types of reactions, we can call them electron transfer reactions, or more commonly, they're called redox reactions. And they're called redox because there are two processes that take place as we are doing these reactions. One of those processes is called reduction, and one is called oxidation. So this is just a smashing together of those two terms, and we'll learn about those things a little bit later as well. So let's talk about oxidation numbers. Probably one of the most important concepts when doing electrochemistry. Assigning oxidation numbers to each element within a redox reaction helps us identify that we have a redox reaction, and it also tells us what's happening to each element as we go from reactants to products. So let's look at an example here. We've got magnesium plus 2HCl goes to MgCl2 plus H2. Now we can see that magnesium is losing 2 electrons, so we say that it is oxidized, and we would also see that the hydrogens gained 1 electron, and so they were reduced. If we look at charges, this is where we can see this. So we see that the magnesium here has a 0 oxidation state. In our HCl, we would say that the hydrogen has a +1 and the chlorine would have a -1. These are the charges that we would get from the periodic table. Turns out they're also the oxidation states. Very commonly, those values are the same. Now, as we go over to the products, we see magnesium is now part of a compound, and so it has a +2 charge. Your chlorine still has a -1, but your hydrogen in its elemental state has a 0 oxidation state. So our magnesium went from a 0 to a +2, lost 2 electrons, and anytime something loses electrons, we say that it is oxidized. The hydrogens went from a +1 oxidation state to a 0 oxidation state, and so they had to gain an electron. When things gain electrons, we say that they are reduced. So we have a couple of acronyms that we use. One is oil rig and one is Leo goes GER. They both do the exact same thing, so just find one that works best for you, and you can always use that one. It's not a situation where oil rig is used in some cases and Leo goes GER is used in other cases. They're both identical and they're used exactly the same way. So we mentioned that this term redox is really a mashing together of the terms reduction and oxidation. And the reason we do this is because these two types of processes have to occur as a pair. If something loses electrons, then something else has to gain them, because we can't just make electrons disappear during the course of a reaction. And vice versa, if something is gaining electrons, they had to have come from somewhere. They can't just appear from nowhere. And so we have to have something else losing electrons. So oxidation and reduction always must occur as a pair within a reaction. So anytime that we have that type of reaction, a redox reaction, we can split the overall reaction into 2 half reactions. One of those half reactions is going to be the oxidation half reaction. One of them is going to be the reduction half reaction. So let's look at an example here. We've got zinc plus copper 2 plus goes to zinc 2 plus copper. Okay, we see zinc is losing 2 electrons. If we look at the oxidation states, we see that zinc metal was in the 0 oxidation state there. And with a 2 plus charge, it also has a 2 plus oxidation state, so it lost 2 electrons. So that means it was oxidized. And our copper 2 plus here had a plus 2 oxidation state when we started, and then it had a 0 oxidation state when we finished. So it must have gained 2 electrons, and so that is my reduction half reaction. So we can write our 2 half reactions. Notice that our half reactions now contain electrons. We've got our 2 electrons right there. And so we have zinc goes to zinc 2 plus 2 electrons, so that's oxidation. Electrons will always be in the product for an oxidation half reaction. And for our reduction half reaction, we have copper 2 plus 2 electrons goes to copper metal. And so for a reduction half reaction, your electrons will always be in the reactant because it is gaining electrons. Now, one of the most important things that we have to be able to do when working with redox reactions is we have to be able to balance the reactions. So we have to take into account a couple of different things. We have to balance the mass like we always do. We have to have the same number of each element on both sides of the reaction, both reactant and products. But we also have to take a look at the total amount of charge on both sides, and that is because we have to account for the electrons. Since we know we have electrons moving back and forth, we have to make sure that the electrons are balanced and that we haven't lost any in the process of our reaction. If we look at this reaction here, we have iron 3 plus aluminum goes to iron 2 plus aluminum 3 plus. At first glance, it might look like it's balanced. We have one iron on each side, we have one aluminum on each side. However, if we were to count up all the electrons on both sides, we would see that in going from reactants to products, we actually lost a couple of electrons, and so this reaction is not balanced. So when we're balancing redox reactions, we often see that they are in acidic conditions or basic conditions, and this is something that you have to be told in the reaction, or at least given some clue. You can't just be given a reaction and say, go ahead and balance it. So normally you'll see verbally or some kind of indicator that your reaction is acidic or basic in its conditions. So when we have an aqueous reaction or an aqueous solution that the reaction is taking place in, and we have acidic or basic conditions, the presence of any H+, H2O, or hydroxides all have to be accounted for because they do get involved in the reaction. So we need a way to balance the oxygens and any oxo anions. So something like a sulfate ion, SO4, a perchlorate ion, ClO4 minus. All of those show up, and we have to make sure that we have ways of balancing any of the oxygens present in the reaction. So let's take a look at our steps. And these are very important steps to be followed in the exact order that I'm giving them to you here. We'll look at balancing a reaction in acid first. So we'll go through the steps and then we'll go through an example. So first thing we want to do is to write the unbalanced net ionic reaction. Many times you'll be given a full reaction, and that's fine too. You can use that as well. It doesn't have to be a net ionic. But let's go through and look at this example here. So we've got iron 2 plus Cr2O7 2 minus goes to iron 3 plus and chromium 3 plus. And we can see that it's not balanced just right off the bat. For one thing, we have 7 oxygens there in our dichromate ion, and we have no oxygens in the product side, so we're missing some oxygens, and we certainly can't have that happen. So we write the unbalanced reaction. We separate the reaction into 2 half reactions. And in order to do that, you really just need to look at the main species that are present. So we can kind of guess here that we're going to have an iron half reaction, iron 2 plus going to iron 3 plus, and then we're going to have the half reaction of the dichromate ion going to chromium 3 plus. So those are our two half reactions that we can write down. So we have iron 2 plus goes to iron 3 plus, so that's our oxidation half reaction. It's not important that you know that that's the oxidation half reaction. That doesn't play into our process one bit. And then our reduction half reaction is our dichromate ion, Cr2O7, 2 minus, goes to Cr3 plus. So we've got our half reactions now. Now the first step in balancing is we balance any elements other than oxygen or hydrogen. Our first half reaction there is fine because it just has one iron on both sides. But in the second half reaction, my reduction half reaction, notice that I've got two chromium atoms and only one chromium atom there. And so my chromiums are not balanced. So in order to balance that, I have to put two chromium ions on that in the product side. So now my ions are balanced and my chromiums are balanced. Okay, so now that step is done. The next step is a kind of a two-stepper. We want to add water to balance oxygen atoms, and then after we balance the oxygen atoms with water, we add H plus in order to balance any hydrogens that are in there. It is important that you do those two things in that order. First balance the oxygens with water, then balance any H's with H plus. And so in that first reaction, we see that we have no oxygens or hydrogens, so we don't need to worry about that. But that second half reaction does have some oxygens. So in order to balance the oxygens, we had to add 7 water molecules. Each water molecule adds 1 oxygen, so that gives me 7 oxygens in the reactants and 7 oxygens in the products. Now if we look at the hydrogens, we see that we have 14 hydrogens in 7 waters. And so in order to balance those, I have to add 14 hydrogens in the form of H pluses on the other side. And so now as far as atoms, I've got 1 iron and 1 iron on the top. On the bottom, I've got 14 hydrogens and 14 hydrogens, 2 chromiums, 7 oxygens, and 7 oxygens. So we are now mass balanced on both sides. We're going to take that and go to the next slide. Next thing we're going to do is we're going to balance the electrons using charges. So we have to make sure that the charges on both sides of each half reaction is equal. In that first half reaction, we see that we've got a 2 plus charge here and a 3 plus charge here. And so that's not balanced. So in order to bring a 2 plus down to a 3 plus, I need to add an electron on the product side on that right-hand reaction. Okay. Now on the second half reaction, I've got 14 pluses here and 2 minuses. So that adds up to 12 pluses net. And then over here on my product side, I've got 2 3 plus charge species, and the water doesn't contribute any charge. So that has a total of 6 pluses. So I have to bring down my higher number of pluses by adding some minuses. And so I need to add 6 electrons to that reactant side to equal out the charge. So my total amount of charge on the reactant side would be 6 pluses, and on the product side, also 6 pluses. Okay, now we want to be able to add up our half reactions. And so in doing such that, we're going to be able to add our 2 half reactions together so that the electrons will cancel out. And so in order to do that, we have to multiply each half reaction by some factor so that the number of electrons on both half reactions is the same. Notice also I want to point out that I have one half reaction where electrons are in the reactant, in the product, and one where they're in the reactant. Okay, that's very important. That should always happen. If you balance your half reactions and you have electrons on both sides, or on just one side, I should say, so both half reactions have in the reactants or both in the products, you've done something incorrect, and you need to go back and figure out what the correct step is going to be. So let's take a look at how we do this. We've got a 1 and a 6 for electrons, and I like to teach it by finding the lowest common multiple between those two values. So the lowest common multiple between 1 and 6 is going to be 6, and so we want to use 6 electrons. Okay, in order to get 6 electrons on the upper half reactions, we just need to multiply that top reaction by 6, and that gives us 6 iron 2 pluses, 6 iron 3 pluses, and 6 electrons. The bottom reaction, we just need to multiply by 1 or leave it the same because that gives us the 6 electrons that we started with. Okay, now we're going to add the two reactions together. Anything that shows up on both sides can be canceled out. Your electrons should always cancel. Okay, that is always. Okay, you should never have electrons left over. So you can see our electrons are going to cancel out, and that's really the only thing we have canceling out here. In other types of redox reactions, sometimes you'll have H pluses canceling out, sometimes you'll have waters canceling out. It just depends on the reaction itself. Okay, so as we saw here, our electrons will cancel there, and what we're left with is 14 H pluses plus the dichromate plus 6 iron 2 pluses goes to 6 iron 3 pluses plus 2 chromium ions plus 7 waters. If you checked each individual atom, you'd see that we're completely mass balanced. And if you add up the total amount of charge on both sides, you would find that the charges on both sides are exactly the same, which means that our number of electrons is completely conserved. Okay, so verify that atoms and total charges balance. Now, that was balancing an acid. We mentioned earlier that we can also balance our reactions in base. There's a couple of different ways of balancing a redox reaction in base. I find one of the methods a little bit difficult, and I find one of them a little bit easy. Thankfully, our book and the way I prefer to teach it is what's in the text. So they work together there. So the first thing we do is, even though a reaction says that it's balanced in base, we balance the reaction as if it were in acid. Okay, once we've done that, then we finished balancing it in acid. Then what we do is we add OH ions to both sides of the reaction to neutralize the H plus ions. So in other words, I need to add the same number of OH ions as I have H plus ions in my final balanced reaction. Okay, any of the H pluses and OH minuses that are on the same side will combine to form water, and then chances are you've got water on both sides of the reaction. You cancel out any H2O that's common on both sides, and then you're done with your balance. So let's take a look at an example. So we're going to just look at the previous reaction that we just balanced and say, rather than balance it in acid, let's balance it in base. Now, we still would have reached the exact same point that we did in the previous example, because the first thing we always do now is to balance it as if it were an acid, but now we're going to change it to be in base. So this is my balanced reaction in acid, well, one that we just did. Okay, now we have 14 H pluses on the reactant side. That means I need to add 14 OH minus ions to both sides. Now, the reason we add it to both sides is to keep the balance. Right now, we have a perfectly balanced equation, and as long as I add the same thing to both sides, products and reactants, my reaction will remain balanced. So I'm going to add 14 OH minus ions to both sides, and those are going to neutralize the 14 H pluses on the left. So there we go. We've added our hydroxide ions. Okay, now over on the left-hand side, the 14 OH minuses and the 14 H pluses will combine to form 14 waters. Okay, so there's our 14 waters. Notice that the OH minuses on the product side had nothing happen to them because there are no H's on that side. Okay, so now notice though that I have waters on the left and I have waters on the right. Okay, so I have to cancel some of those since I have 14 in the reactants and 7 in the products. 7 of those are going to cancel and leave me with a net 7 waters on the reactant side, and I still have 14 OHs on the product side. and that is my balanced reaction in base. It's a very simple method to balance in base, much simpler than starting from scratch all over again. So that's how we balance our redox reactions, both in acid and in base. Here's one I'd like you to try. Balance it in acid. Actually, if you want, you can balance it in acid and then try it in base. I will post a solution to this on either on Eleum or on YouTube.